Next speaker is Dr. George Pess, Program Manager for the Watershed Program at NOAA Northwest Fisheries Science Center and an Affiliate Associate Professor at the University of Washington School of Aquatic and Fisheries Science. And I will share screen. So I gotta find you in this list of 87 people now we've got, which is great. Okay, George, you should have a window pop up and we can see your screen as soon as you accept it.
Okay, I am accepting it as we speak.
And there it is.
Okay, and then I'm going to go to slideshow, and hopefully this is going to go to slideshow. Is it gone to slideshow yet or no?
So we still see the full screen. It might be on a different monitor of yours where, I mean, we still see the, there we go. Now it's slideshow.
Okay, thank you. So thanks again for inviting me, and thanks for everybody coming today. So the title of my talk today is How Much Restoration Does It Take? And I'm really focusing on more empirical evidence for the scale of restoration needed to see the salmon population increase. So Tim's talk was a great primer to this, and we'll go into some of the real life examples of what people have been able to measure. So this kind of breaks down into three different questions. How much is enough to actually identify a salmon population response for a typical suite of stream and watershed actions, and how long does that response actually take to be seen? How many years in this case? And do we have any successful examples? And the short answer to the last question is yes. So I'll go over two examples for you. But again, just to remind you that when Tim focused on this quite a bit, and I think it's really important, is that depending on the species, habitat is utilized differently. So for the same kind of change for these different habitats, whether you're talking about tributaries or main stem, side channels in floodplains or beaver ponds or the estuary, you're going to see a different kind of response as a function of the species. And then also within that, the life history diversity within the species. So one question that we asked, it's been over a decade ago, is when we're looking at empirical evidence, can we actually identify a salmon population response from a typical suite of restoration actions? So this is work that we did with Tim and Phil Roney and Sarah Morley, where we looked at basically existing salmon density data from different kinds of studies to estimate the potential response in a much more simpler form than what Tim talked about with the life cycle model. So we tried to scale up from these density effects to the population level and see if we actually were able to see a signal. And then we apply different restoration scenarios to determine a population level response. So similar to what Tim showed you, we asked this kinds of questions, and then we apply a mean fish response to the different watershed strategies that people have utilized. But really what we did essentially is look at kind of full restoration versus what people typically, or watershed groups typically do. And then we applied a Monte Carlo simulation to look at the distribution of potential responses. So the data that we used was, a lot of it was our own data that we collected from empirical studies looking at in-channel wood placement, boulder structures, barrier removal. Let me just do one thing here, folks. I'm going to just get a laser pointer for myself. So yeah, log placement, boulder structures from specific projects in Southwest Oregon, looking at barrier removal in Puget Sound, plus constructed log jams, floodplain rehabilitation in certain areas of Puget Sound, and then also groundwater channel rehabilitation. So then we actually said, okay, well, what kind of potential response did we actually see from these different restoration actions? And this just gives you an example of some of the data that we had for coho and steelhead. Again, not many sites for some of it, but this was a while ago. But it gives you an idea of what kind of potential response we saw from the different restoration actions. And then we asked, well, how much habitat do we actually have in a typical Puget Sound watershed in terms of streams, rivers, function, stream sizes, a large stream, basically main stems, medium somewhere between 5 and 20 meters, and then less than 5 meters in terms of bankful widths. And then how much floodplain habitat do we have in the form of side channels that are existing versus lost versus sloughs. So we tried to make it as real as possible based on what's actually out there. And then we asked, well, what is the typical production that we see for smolts in these different watersheds? And this is what we had from data that we gathered from about a dozen different, or actually more than that, about 15 different watersheds in Puget Sound. And then we asked, well, what do people typically do in these watersheds? What we found was that wood placement and barrier removal were pretty common in some of the smaller streams. There was definitely boulder weir placement in some areas, and then log jam reconstruction. And in the floodplain habitats, we saw that people tried to develop groundwater channels and floodplain reconnection. And so you have to keep in mind, this is all before kind of the stage zero concept kind of came to light. And then we said, okay, well, if you take a typical Puget Sound watershed, and actually in terms of size, I would just say the typical Puget Sound watershed is the Stillaguamish River here, shown to the right. We said, okay, if we actually did full restoration, what would that actually mean to potential fish production? And what we found was that we got obviously a distribution based on the Monte Carlo, but on average, we saw basically 100% restoration resulted in almost a 100% increase of potential fish production from these basins. So again, remember the current production was around 230,000. So that was a typical, in a typical watershed, we'd see a 100% increase for coho. And for steelhead, about the same thing. So going from about 22,000 to about 50,000 potential smolts coming out of the system with a 100% increase based on the numbers that I showed you. And just as Tim showed you, it's going to vary. The restoration action will, and the proportion associated with the response will vary as a function of the restoration type and how these fish actually utilize these habitats. So if we look at coho, for example, the vast majority of the response that we saw potentially comes from floodplain actions, whereas for steelhead, as Tim showed you too, most of it was in channel, whether it's small streams, medium streams, or large streams. So then we asked the question, well, that is in a kind of idealistic case, what do people typically do on an annual basis? And so what we found was that if you look at the average Puget Sound watershed and the restoration actions associated with it, about 6% of the total area is typically restored in a given year. So if you translate that, that's several kilometers of in-stream and floodplain habitat and maybe tens of kilometers of barrier removal in a given year or a couple of suite of years. So when you actually translate that 6% increase, what does that actually mean in terms of actual fish numbers? And it's not nearly as much. It's an order of magnitude less. So about, on average, 15,000 more potential coho smolts. And that's potential. That's not actual. And then for steelhead smolts, it's a little over 1,000. So again, not a surprise if you're only doing 6% of the total area that needs to be restored. But I think it's an important point because as Tim was showing you, that the scale of the restoration action is a real driver in the response. And that's something that I'm going to keep kind of talking about throughout this whole talk, which links back to the talks that you're going to hear after this in terms of the stage zero restoration. So if we look at the kind of breakdown in terms of where this response is coming from, again, the 100% scenario shows that most of it's coming from the floodplain for coho and most of it's coming from in stream for steelhead. But if we look at the 6% restoration scenario, it's a little bit different. In other words, barriers and floodplain become more important for both species when you're doing a limited amount of restoration action. So, which is kind of interesting in terms of just thinking about this. So a little bit different in terms of the distribution. So in summary, what we found was that we had about almost 230, a little over 230,000 estimated smolts coming out of a typical Puget Sound watershed, 22,000 steelhead. If you did 100% scenario restoration scenario increase, you're getting a double of that for both. And then for 6% of the watershed, you're seeing quite a bit less. So there's a lot of limitations with what we did here. This is a pretty simple exercise, and there's a lot of variability in the data. And so that's one of the reasons why um, I showed you those distributions. We did not quantify the components of that variation to kind of break that up a little bit. And we really only focused on one metric, and that's density. So Tim's taking it to the next level with looking at survival and productivity. And we had to make multiple assumptions to translate those densities into potential production. And I guess one take-home message that I would say is that when you're actually doing this, if you're actually trying to monitor this at a population level, you really need to look at multiple metrics besides density. You need to look at occupancy, looking at multiple life stages, growth, and survivorship, because that's how you actually get some of the other responses that you may see. So in summary, basically, full restoration resulted in an over 100% increase in potential production. But what we saw in terms of what typically is restored, it's really about 6%. And what we saw then for increases was about the same. And there's a lot of variability with the data that I showed you. So basically, you need to see a signal of 25% or greater to actually deal with that variability. And the signal that we saw was about 5 to 6% for a typical watershed. So not enough to really see a change in adult salmon returns. So the second question that I posed to you was, how long does it take to identify these responses? And there needs to be some context with this question, because it's really about, well, what's the question that you're asking, and what's the scale of the question that you're asking, and what are you actually measuring, and what kind of inference level, what kind of level of certainty do you need in terms of your answer? And then that will also be impacted by your study design, and then asking the question of, if it's not a statistical population level response and you're looking for a biological one, what does that actually mean? So there's a lot of things that go into this question of how do you identify a population response. So the most important thing is really the questions that you're asking and the scale at which, or the extent at which you're asking. So you could be asking at the reach or water scale extent. And what people typically ask is, what is the effect of one project on watershed conditions and salmon populations, or at the reach scale? And that's a tough one to answer, because you're really not going to get a population level response with that. Really, the question that you want to ask a lot of times, and what I just showed you, is what is the effect of projects like a certain type of project at the on local conditions or fish abundance? Or if you're really scaling up to the population or watershed scale, what is the effect of a suite of projects on watershed condition and salmon population, which is the question that Tim was focused on, and the question that I just showed you that we focused on with the simple example. Now, one of the things to keep in mind is that what are the parameters that you're actually measuring? Again, what I'm talking about here is, if you're trying to actually do this on the ground, there are things that really have a direct and immediate effect on fish, such as the connectivity of a watershed, which is what Tim focused on and what we're focusing on for this entire session. And there's also things such as restoring in-stream flow, which is one of the questions, and then in-stream habitat. But a lot of the things that we do are indirect and not necessarily immediate. And even the things that we do that are direct, they may have a lag effect. Case in point, barrier removal, like dam removal that we've seen on the Elwha. So I want you to keep this in mind as we move forward, and as you think about if you're actually trying to plan something like this. So the inference level, what's the level of certainty that I want? And the thing that always we want to keep in mind is that there's always going to be some sort of variability. So what you're trying to do in most cases is separate out the signal from the noise. So in other words, the signal being the treatment effect of the restoration actions, and the noise being the natural variability. And then from a kind of a statistical point of view, what's the certainty level in terms of confidence interval? And then what's the power to actually detect the change? So those are all things that you want to take into account if you're actually setting this up in terms of a study design. So then you can ask the question, well, what kind of study design would I need to actually garner a salmon population response? And these are typical ways of thinking about this. And a lot of times we think of the treatment and the impact at different scales, like what has been restored versus what is the control which hasn't been restored. And then also Tim talked about kind of the ideal conditions or the reference or historic conditions. So these are all things to consider in the study design that ostensibly translate into things such as a before after. So this graph shows you a really simple case where you may have a before set of data in terms of fish density or fish production, and then you have a restoration action, and over time you see an increase. You may get more inference, so to speak, or understanding of what's happening if you actually have a control during that time, so you can actually start parsing out the signal from the noise, if you will. And then you may get even more inference if you actually include a multiple before after. So in other words, you have one treatment and you have multiple controls. Um, and then what we're typically relegated to, which is not going to get you a population response, but can tell you something at the local scale of what you're seeing, is extensive post-treatment. So in other words, we're not necessarily measuring the population, but we're going in and we're saying, okay, well, we know that before we had a density of X or a density of Y for these different habitats or these different species, and now we're seeing something different. So when you kind of pool all that together in terms of study design, there's certain study designs, basically when you're looking at the watershed scale, like before afters or before after control impacts, that will give you a population level response, but it takes time. And that's where we're going with this. It definitely takes time. Whereas for the post-treatment kind of analysis, it may not take as much time, but you're not going to get a population level response. So those are things to keep in mind. And the reason I bring all this up is that we kind of forget about this, because most of the time what we're challenged with, and we're part of this as well, is, well, people give you money. They say, we want to see a change in salmon populations, and you've got typically 5 years or less to do that. And the short answer is that's highly unlikely that you're going to be able to do that unless something really dramatic happens. So when people have actually looked at this, where we've done power analyses and said, okay, well, how long will it actually take to detect a change if we have a certain study design, such as a before or after? Let's say, for example, steelhead at different life stages, steelhead at 1+ and steelhead smolts. And this is from the Oregon coast, Salatsi et al., where they had a certainty level of 95% and a power to detect a change of 80%. And what they found was that basically they needed a 2 to 3-fold increase to get a signal, if you will, in the ostensibly in a couple of decades, which is a long time in terms of funding, but that's what you would see, at least from a statistical standpoint. So when you do these power analyses, it gives you a lot of understanding of what it takes for different metrics. So remember about that, about the parameters that I mentioned. So these are specific parameters here. So we did the same thing in the Elwha. Just for those that don't know, I've been involved in the monitoring of the Elwha dam removal. And so that is obviously a large magnitude change in terms of watershed opening up over 90% of the habitat. And we looked at this from a power analysis perspective, and we said, for different metrics that we think are important, what do we need to see in terms of an effect size? So the magnitude of change, in other words, what's the treatment giving us in terms of increase, and how many years is it going to take to actually see a signal? For adult Chinook returns, we've seen a pretty dramatic change in the number of fish, not necessarily due to the dam removal, but a combination of things. But even so, it's going to take a while for us to be able to say statistically that this is due to the dam removal. And the number of years seems a lot, but you have to think of things in terms of generations of fish when you're talking about salmon. So how many generations are we talking about? This is about 3 to 4 generations of salmon returns. And that's pretty typical for restoration actions. So if you really want to see adult return numbers, it takes longer than it would for smolts, than it would for habitat conditions. So that's kind of a typical rule of thumb. So in summary, I guess there's really no ideal study design when we're thinking about the question of how long does it take to identify it. There's strengths and weaknesses with each. And really, the more time and the more you can put into it, the better the inference is going to be. And I think power analyses are pretty important because they identify different parameters. So when you're going back to your funders and you're saying, well, we want to measure certain things, you can actually manage their expectations and maybe kind of not focus them on adult returns right away, but say, there's other things that we can measure that come sooner from a population level response than come later. And the most important thing to keep in mind is that when you're actually trying to do this in real time is that you're going to make mistakes, and just make sure that your mistakes are not fatal to the questions that you're asking. So now I'm going to shift and talk about some real world examples of how long does it take to actually identify a population response. And this is just some work that I did as part of my PhD dissertation looking at patterns and processes of salmon recolonization. And what we have here on the x-axis is years since colonization occurred, and then the percent increase in adult population abundance. And this is for larger scale kind of barrier removals, and I'm using the term broadly because we have things like, for example, the Fraser River, where we're looking at pink salmon increase due to the removal of a rock slide at Hell's Gate back in the early 1900s, or the deglaciation of Glacier Bay. Then we have more real examples such as, fish passage ladder on the Cedar River in Washington State. So the bottom line is that we saw kind of a 100 or to 1 to 4-fold increase in population in a matter of about approximately 15 years. So again, instead of thinking of it in years, thinking of it in terms of salmon generations, and that's anywhere from 2 to 4 years of salmon generation there in terms of population. There's also been examples looking at long-term studies of what actually has happened with resident trout. We had a resident trout question before, and some work by White that they followed up on in Colorado basically showed that 20 years after wood placement that they saw an increase in adult abundance immediately that actually stuck around for about over 50% increase 21 years later. But they looked at multiple things. They looked at adult trout, but they also looked at juvenile trout. And what they found was that there was really no change in juvenile trout. And part of this is because when you're thinking about the wood placement, it's not necessarily influencing that life stage as much as other life stages. So this is a great example of how if you use multiple population parameters, you might start actually getting at what may be the limiting factors if you don't know what the limiting factors are for populations. So now I'm going to focus on the last question, and the question is, are there any examples of success that can help groups, assist groups in implementing stream and watershed restoration actions and identifying a population response? And there's two that I'm going to give you. The first one is from work by Oxton et al. In the Chilliwack River in British Columbia, which is a tributary of the Fraser River. And what they did there is reconnect a bunch of floodplain channels in the Chilliwack Vedder River system. And they did that kind of with more traditional approaches of channel construction, but it included spawning and rearing habitat. So the bottom graph you see here is basically showing you some of the stuff they actually did, and they constructed about 5 projects between 1996 and 2000. In terms of what they measured, they had a downstream count of adults at each of the channel outlets, weir counts, as well as a minnow mark recapture program in each of the side channels, and they recovered marked fish at the downstream end at this ST, which is the screw trap. And they accounted for use of the main stem of fish that moved from the main stem into the floodplains. And I'll tell you why that might be important and link back to Tim's talk. But they actually tagged fish with pit tags there, and they knew the capacity of each of the floodplain channels that they built. So they actually measured the capacity of the for different life stages, and then they looked at what was observed. And what they found was that basically they saw a third of all the coho that were coming out of this system produced in the new side channels. So that's a pretty significant change for what was happening before, and that there was a 40% higher overwinter survival in the off channels, and that included fish that were going from the main stem to the off channel. So if you remember one of Tim's slides, he showed the difference between the survival, and it was about 43%. So this is pretty similar to what he showed. And the other thing that they did I thought was really interesting is that a lot of times people ask the question, well, is this more cost effective? Is it more cost effective to do habitat restoration work than to supplement with hatcheries? And the short answer is, for this example, they found that it was much more cost effective to actually do the restoration work and allow kind of nature to take its course than to supplement with hatcheries. So why did it work here? That's a question that people ask. Well, one of the reasons is that they focused on coho salmon and they actually got the limiting factor right, which was overwintering habitat. They did the restoration action at the appropriate scale. In other words, they did a lot. And they also connected habitat between life stages. So in other words, they didn't just open up habitat, they thought about how the habitat was going to be seeded as a function of the preceding life stage. And I call that parents dropping the kids off at the pool. So adult seeding downstream juvenile habitat. And that there was a survival increase for all juveniles, including the main stem resident fish that migrated into the connected or created habitats. And this picture is not from the Chilliwack Vetter. That's a side channel of the Elwha. So the next one, a lot of you might be familiar with, and this is thanks to Tim Copeland and others who gave me permission to show you some of the results here from a recent paper they just published on the Pacimoroi, where diversions were reconfigured in the basin that allowed for basically habitat expansion into 12 plus additional miles of kilometers of habitat. And the hypothesis was that if you expand the spawning habitat, you would actually create more juvenile rearing habitat as well. So then the question becomes, well, what do you get with that? And what they did in terms of monitoring is that they did multiple pass Chinook red salmon surveys. They looked at the density of juvenile salmon and with snorkel surveys and index regions, and they quantified the number of outmigrating Chinook salmon using a rotary screw trap downstream. And they also used the PIT-TEC technology to look at survival and estimate abundance using mark recapture techniques. So the question is, how had the restoration affected spawning distribution? And what you see here is that it's important to note that the number of salmon reds did not necessarily change, but there was a 42% increase in amount in the distribution of that habitat. So you saw the densities actually shift, and you saw an increase in areas post-restoration that you didn't see fish before. So it was a redistribution here. And what you saw with that redistribution is you saw places actually get densities of juveniles that were not seeded before. So ostensibly, this is kind of thinking about in terms of like a barrier removal almost in many ways. But now you had distribution into newly connected areas. And then the juvenile densities in the reconnected area were correlated with the red densities from the previous year. So then the question becomes, well, what did you see with the before and after? So here you're looking at two graphs. One is the emigrants at the rotary screw trap, and then the productivity on the right of emigrants per female. So that's ostensibly smolts, and not necessarily a statistically significant change in the emigrants at the rotary screw trap, although you saw an increase. But you did see a statistically significant change in terms of the productivity or the emigrants per female. But either way, you saw an increase, and I think that that's the most important thing here. So in summary, what you saw here was an increase in accessible habitat by 246%. And that's an important number to think about, because when Brian and Paul and others talk about their exercise, you'll see what kind of percent change in terms of accessible habitat it may be. And they looked at multiple Chinook life stage metrics, which I think is really critical. They looked at the adults and they looked at juveniles. And again, this concept of connectivity of how the adults got into new habitats and used those habitats and what that means for juveniles. And the large increase in accessible stream length appeared to reduce some of the density dependent effects that happened downstream. And you're seeing an upward trend in smolts per female here. And really, it's about the Chinook population becoming more efficient and resilient. And I think that's a really important point, because we talk about resiliency and efficiency, and what does that actually mean? And I think this is a great example of how to quantify that. I think at the end of the day, a couple of take-home messages are pretty important. That you need to do a lot of restoration to see a population signal. So that could be one project like a dam removal that opens up a lot of habitat, or it could be a bunch of projects across the landscape. But a lot of times we want to see a population response with a small suite of restoration actions that really don't amount to what actually needs to be done. And I think it's really important to understand that, because of the variability in fish production that we see, I think it's really important to understand that doing a lot does make a difference, whatever that may be, and that it takes years to decades to actually see a population level response, even under the best circumstances. So regardless of the study design and everything else, it takes time. But I think that if you're using multiple metrics, you can actually start seeing a signal for a population response sooner. In other words, you could see what's going on with the juveniles or the redistribution, and those set up the stage for ultimate change in adult numbers. And with that, I just want to say thanks, and I have several references if people are interested. So thank you.
Thank you, George. So there were some questions that came up in the chat box. I don't know if you had a chance to look at those, but Kate asked earlier on in your presentation, what are groundwater channels and are they occurring naturally?
So that's a good question. So what they define as groundwater channels, Kate, are basically seeps or springs, and they do occur naturally. But a lot of these groundwater channels that they were monitoring in the Chilliwack Vetter system were basically kind of constructs of what basically what engineers perceive as a good side channel. So they're not necessarily that natural, but what they did well, I thought, was that the reason they focused on groundwater channels is they wanted basically flow attenuation, higher flows in the summer, lower flows in the winter, and that's why they try to kind of create a stability, if you will. So that's how they defined groundwater channels. And then the next question is, how might forecasting for population response be impacted by competing species that might share preferences for improved habitats? It's a really good question. For the examples that I showed you, I didn't have any data that showed what happens to competing predators that are both natural and invasive in these off-channel habitats, but I know that that's a question that's being posed in some areas, and I might even defer to Tim on this one. I know that Julian Olden might be looking at that in the Chehalis, Tim, in terms of like bass and other things, but I don't have much data on that.
Yeah, this is Tim. Yeah, they are trying to look at that in the Chehalis and other places, Sacramento and different river systems. We didn't have mortality numbers. We didn't have a way to put that into the model, even though it's definitely a big concern in places like the Chehalis that are pretty warm and you have lots of non-native predators. And then in terms of competitors, if they're not actually preying on the juvenile salmon. So we did not evaluate any of that, although if you had data from sites like that, you could. Our data were from sites where we had all the salmon species coexisting, so that kind of competition is accounted for, but not other non-natives.
I don't see any other questions on the chat. Does anybody else have any questions? Oh, there's one. Based on the idea, the scale of restoration implemented is important to get a response. Should focus on lower cost practices, which are more likely to be scalable, beaver dam analogs or PALs? That's a good question. I don't know if I have a perfect answer for you, but it's a way to go. So in other words, instead of going the route of like doing a large scale project that might take years to actually implement versus one where you could do them, over the course of many years. I don't know what the answer is to that because we never really kind of looked at it from that perspective. I guess my personal opinion on this one is that I kind of tend to the go big or go home. I'd rather see um, a larger project that might take years to implement um, um, than something else.
I like that. Go big or go home. Okay.
Yeah.
So we have a little bit of time if anyone has any other questions, and feel free to unmute your microphones, everyone. You can use the chat room, of course, but we do want to hear from people too. So any other questions here for George before we move on to the next person?
Gene, I actually had something to say about the life history reawakening question that Tim got. I did have an example of that, a real life example. So the question before, if everybody remembers, was like, do you see, can you model new life history strategies? And from an empirical perspective of what we've seen, some examples, yeah, you get reawakening life histories we may have seen in the working on is the reawakening of summer steelhead there. So I don't know how many people are familiar with the concept of the pre-migration locus marker genetically that spring chinook and summer steelhead have in certain areas. But what we found in the Elwha is that fish that were basically resident trout or
Oh, George, can you hear us? Your microphone faded out there. Sounds like there might have been a wire connection or something, but we lost you, George.
Yeah, I'm still lost. Hold on.
Okay, now I can hear you.
Can you hear me now?
Yes.
Okay, because it says that I'm muted right now.
No, now we can't hear you. Maybe there might be a lag. I'm not touching the mute button though.
Can you hear me
Okay.
now?
Yes.
Okay, sorry about that. I don't know what happened. But anyway, the bottom line is we saw a reawakening of summer steelhead there to the point where we had a couple years ago a population estimate doing mark recite of 900 summer steelhead. So we went from maybe 2 or 3 to 10 or less summer steelhead to over 900 in 4 years, simply because that life history strategy was bottled up above the dams and now has been able to kind of reawaken with the connectivity. So you can get, with large scale restoration actions, depending on the context and the situation, you can get, different life history strategies that make a huge difference in terms of the overall abundance numbers.
And Paul says perfect examples. Thanks, George. Anything else for George here?